In this project, the airflow field corresponds to a flying bird has been investigated by ANSYS Fluent software. The noted problem has always been the center of attention from at least two perspectives. The study of bird aerodynamic and their flying mechanism has primarily been useful for companies involving the production of flying equipment. Furthermore, environmental scientists are also using these type of investigations to estimate the spread of birds' illness during their migration period, in which they were flying in a group. On top of the investigation for the CFD simulation in this project, we're going to show you how to create the geometry related to this project using ANSYS Design Modeler software, and then we will generate the mesh over this geometry, meaning the bird itself and the fluid domain around it, using the ANSYS meshing software. Alright, to start performing the simulation related to the project of airflow passing over a bird's body, what we're going to do first is that we are going to select this fluid flow block and then simply drag it into a blank space inside the workbench environment and just leave the left click on the mouse. After that, you may simply right click on the geometry to, for example, select new design modeler geometry, or you can simply double click on it and wait for the geometry software to open up. Alright, as you can see here, the ANSYS Design Modeler software has opened up, and the first step in this project is to simply import the geometry related to the bird. As a matter of fact, we have taken this geometry and downloaded it from the GrabCAD website. So what I'm going to do simply here is that I will simply select on File, go over Import External Geometry File, and as you can see here, I have an external geometry file with the name of bird geometry. Click on it and then click on Open button, and simply I will click on Generate button. Now you're gonna have to wait for some time until the geometry is read by the Design Modeler software. Alright, as you can see here, the geometry of the bird now has been imported into the Design Modeler software, and we can see it right now. The next step is to create a domain around this body of the bird, of course, to simply define the fluid domain around it. So I can simply go over Create, go over Primitives, and I will actually define my domain as a box around the body of the bird. So I will select Box, and on the low left side of the software window, you have to enter values for X coordinate, Y coordinate, and Z coordinate, along with entering values for diagonal X, Y, and Z components. So I'm going to actually start with the X, Y coordinate values, and make sure that you enter the values you can see here in your own software as well. So the value that I'm going to enter here for X is equal to minus 2.5 meter. I will enter the same value for Y coordinate as well, and regarding the Z, we have to enter the value of 4, so that you know, the space behind the bird would be much more than the space in front of the bird, so that they can actually investigate and see the flow behavior after it passes over the surface, or after it passes over the geometry of the bird. Alright, the next step is to define values for diagonal X, Y, and Z component, and you have to actually enter the value of 5 meter for each of these three options here. Alright, as you can see here, I have entered the value of 5 for all of these three options, and now you can see actually a shadow of the defined box based on the values that we have entered here around the body of the bird. As I click on the Generate button, you will see that this shadow will turn into a 3D object. So I will do that, and now we have our 3D object. Okay, what we're going to have to do next is to simply subtract the body of the bird from the fluid domain itself. So what I'm going to do here is that I will go actually over to Create and then select Boolean. After selecting the Boolean command on the low left side of the software window in front of the operation, you have to change it to subtract, as was mentioned previously. As for the target bodies, we have to actually select the body that we are going to perform the subtraction on. So I will select the box body, And as for the tool bodies, since it may be a little bit hard to find the body of the bird under the box, we can actually select it from the part section and simply selecting the solid part. Or another way is to simply select the box body, right click on it, and then select actually hide body. In this way you will be able to have access to the geometry of the bird. So as I was saying, the second way is for you to simply hide the box and then select the geometry of the bird itself. And then you can simply click on apply button under the tool bodies, and in that way all of the needed bodies are selected right now. Regarding another option that is available here, which is the preserve tool bodies option, you can see that by default the no option has been selected, indicating that when actually this no option is selected, the body of the bird itself would become eliminated from the fluid domain. However, if you select yes, we would still have the body of the bird and the fluid domain. However, they are actually subtracted from each other, and they would count as separate bodies. In this project, since we wouldn't want to have the body of the bird itself, so we can simply change this option to no and then click on generate. In this way, actually, you will have a fluid domain in which the body of the bird itself has been subtracted, and actually there is a void space inside the fluid domain with the shape of the bird itself. So I will actually right click on the blank space inside the graphics window and click on show all bodies, because as you can probably remember, we have hidden the geometry of the fluid domain. So as I click on the show all bodies, you can see that the box would become visible again. Alright, there is another thing that you can do here is which is to actually change the state of this fluid domain. As you can see here on the low left side of the software window in front of the fluid or solid part, the solid has been defined by default. So I'm going to actually change it to fluid. This is very much option. This is a very much option for you, and you actually don't have to simply change it to solid or fluid. So it's just an option again, as I mentioned earlier. Alright, that's it for the geometry part. We can simply close the design motor software in order to open up the ANSYS meshing. Alright, as I mentioned earlier, after finishing the geometry, the next step is to simply double click on the mesh button. As a matter of fact, after opening up the ANSYS meshing software, you're gonna have to wait for some time until the geometry, until actually your design geometry would become attached to the ANSYS meshing software. So as you can see here on the bottom part of the ANSYS meshing software, there is this loading bar which shows you whether the geometry has been attached or not. Alright, as you can see here, now the geometry of the bird and the fluid domain around it has become attached inside the ANSYS meshing software. The first step is to define names for different surfaces and boundaries of our geometry. So what I'm going to do here is that I will simply select the face selecting command, as you can see here, and then let's say I would select this surface, and then I would actually right click on it. Before actually going any further, I should mention that when you select the surface, its color would become green, indicating that it has been selected. So as I was saying, after selecting a surface, you may right click on it and then select create name selection option. In this way, you would see that a new window will appear in which it'll ask you for a name for this surface. So let's say I would like to give the name of inlet boundary to this surface. Then I will click OK. For the next boundary that I'm going to give name, I would have to select the other side on the fluid domain. So I will rotate my geometry and then again select face selecting command, select this boundary, right click, and then create name selection, and let's name it as outlet boundary. Alright, These are the two boundaries related to inlet and outlet boundaries. The other surfaces of the box would have to be named as symmetry boundaries, so that we would be able to define actually zero a slip boundary condition over them. So I'm gonna have to select actually the surface face selecting command again, and you can actually select all of the 4 surfaces on the sides of this box by holding down the control key, and in this way you would be able to select more than one edge. Alright, after selecting the 2 edge, you can simply rotate your geometry, and after rotating you're gonna have to again hold down the control key in order to select the 2 left surfaces. So I will simply do that, and now I will right click on them and then use create name selection, and I will name them as symmetry boundaries. Alright, as I click on the name selection part, you can see that the names of different boundaries that I have defined previously are shown here. For example, this would be the inlet boundary. Now this would be the outlet boundary, which is on the other side of the inlet boundary, and this is the symmetry boundary. Okay. Another boundary that we need to give name to is the surface of the bird's geometry itself, because in the next step we're going to perform some mesh commands, and we're going to need these selected surface of the bird geometry itself. So what I'm going to do here is that I will simply select face selecting command again, and simply select all the surfaces that are between for example your view and the geometry of the bird itself. After selecting these 3 surfaces, for example, I will simply right click on them and then select hide faces. In this way you would be able to select the surfaces of the bird body itself. Alright, since we have multiple faces related to the body of the bird, it may be hard for us to simply select each of them by clicking on the surface itself. So what I'm going to do is that I will simply right click on the blank space in the graphics window and then simply use the select all option. In this way, all of the shown surfaces would become selected. However, since some of these selected surfaces are related to the fluid domain itself, I will simply hold down the control key and click on these surfaces. In this way, they would become unselected. Now, if I rotate the geometry, you would see that only the surface related to the geometry of the bird are now selected. Alright, similar to what we did previously to define and give name to different boundaries, I will simply right click on the blank, right click and then select create name selection. And let's say I would name them as bird, and you can see that this surface is now added under the name selection. Alright, another thing that you can do is to actually select the body selection command in order to give a name to your fluid domain. This is particularly beneficial when you actually go inside the Fluent software in order to define the needed material or the correct material for your cell zone. So I will select the box and then name it as, let's say, fluid. Alright, the next thing that we need to do is to define some mesh command for our geometry. So I will right click on the mesh, go over insert and then select sizing. What we're going to do here is that we're going to start by actually creating a face sizing command for actually the surface of the bird geometry itself. So as you can see here, after selecting the sizing command on the lower left side of the software window, the software is asking you to select a geometry. Since selecting the geometry of the bird itself would be a little bit hard, which was explained earlier, I'm going to simply change the scoping method from geometry selection to name selection. In this way, because you already have defined the name for the surface related to the bird geometry once, you would be able to simply select it from the name selection part. In this way, you can easily see that the surface related to the bird geometry are now selected without any problem. Alright, another thing that you need to do is to make sure that you have created a high quality mesh over the surface of the bird geometry, because you want to make sure that you have an exact simulation and accurate results regarding the airflow passing over this surface. So what we're going to do here is that we're going to actually activate both of the capture curvature and capture proximity options in order to make mesh cells smaller and have higher quality regarding the geometry of the whole body. So I'm going to simply change the capture curvature option to yes, and proximity to yes as well. As a matter of fact, by activating these two options, there is no need to change the other settings, and the software will make sure that high quality mesh is placed over the surface of this geometry. Alright, the next command that we're going to use would be the body sizing, which we're going to apply over the fluid domain. So I will simply right click on the mesh, go over insert, and then select sizing again. As for the geometry, make sure that you have selected the body selecting command and click on the fluid domain and simply click on apply. As for the type, make sure that the element size is capped, and regarding the element size value itself, enter the value of 1.1 so that smaller mesh cells are generated for the domain. After that, you may click on the generate so that the ANSYS meshing software would create the mesh over your geometry. As you can see here, you can see the loading bar showing you that the ANSYS meshing is performing the meshing process. Okay, after waiting for some time, you can see that the ANSYS meshing has created the needed mesh over our geometry. As a matter of fact, one thing that you can do in order to make sure regarding the quality of the mesh cells placed inside your geometry is to simply create a section plane. You can actually find this command by clicking on the Home tab and then selecting the section plane command. Alright, so what I'm going to do here is that I will simply select good view and then drag a line, for example, over the middle part of my geometry. In this way, you would see that the geometry would become, divided into two parts in which you can see the inner mesh. After creating a section plane on the lower left side of the software window, the software is actually showing you its specification. If you actually want to see the inner mesh cells in a 3D format, you can simply select this option, and in this way you would be able to see the inner mesh in a 3D format, which is better in viewing. Alright. Another thing that we can do here is that we can actually click on the section plane number 1 and then use the edit section plane and drag this middle part on left or right so that the section plane location would be changed. Alright, I will do it again, and now as you can see here, this is the location where the bird geometry is placed. You can easily see that in this place the mesh cells are smaller comparing with mesh cells in other places of your dummy. Alright, that's it for the ANSYS meshing software. What I'm going to do next is that I will simply close the ANSYS meshing. Okay, now if you see this lighting marker in front of the mesh, all you have to do is just simply right click on it and then select update. Now after some time, this lighting marker would change into a tick marker, indicating that you can move on to the setup part, which is to actually launch the Fluent software. Okay, that is what I was talking about. So the next step would be to simply double click on the setup button. Alright, after creating mesh for your geometry, the next step is to simply double click on the setup button. And you can see that this window, which is the Fluent launcher, will open up, and under the options section you just have to simply enable the double precision. And for the solver processes, based on the number of CPU cores you have on your system and you want to use for this simulation, you can actually enter them here. For example, I have 8 CPU cores which I want to use, so I will enter 8 here, and then I will click on the start button. After that, you're gonna have to wait for some time until the Fluent software reads the mesh and the related parts in geometry. As you can see here, the Fluent software is reading the mesh and the different parts that your geometry has. You can see that it's reading different boundary names for your model. Alright, as you can see here, the Fluent software has read the mesh related to our project. First, we're going to start with the general setup tab. Under this part, under the mesh section, you can see different buttons with the name of scale check, etc. As I click on the scale button, you can see the DOM and extents of your geometry that is shown here. So I will move on to the check button. As I click on the check, you can see that the software is showing you different statistics related to minimum, maximum volume for each of the mesh cells that are placed inside this geometry, and actually it gives you different statistical data related to your mesh. Regarding the report quality, as I clicked on it, you can see that the software is giving you a small report related to the quality of the mesh cells that are present in your domain. As I click on the display button, you can see that in the shown window, different surfaces and boundary names are shown here, which you can actually select or deselect in order to show them inside the graphics window. So let's say I would like to see the bird surface itself and the outlet domain, so I will have to deselect the inlet boundary along with the symmetry. Now as you can see here, only the bird surface and the outlet surfaces are selected. So I will click on display button, and you can easily see that these two surfaces are shown in the graphics window. As for the units part, if you actually click on it in the appeared window, you can see different quantities that are available inside the Fluent software. And for example, let's say if you select any of them, actually, let's say I would like to select time, you can see that the units that are available to the Fluent software for this parameter will be shown here. So I will click on close, and next I will move on to the solver section. In this part, you can see that different assumptions are made for this project. The first assumption is related to the type of solver. Since in this project we are going to investigate incompressible flow, so we have selected pressure based type of solver because we don't actually have any density changes related to the air material itself. Next, regarding the velocity formulation, you can easily see that the absolute format is selected, indicating that we don't have any parts or boundaries or even geometry in our domain which has rotational or translational motion. And finally, regarding the time study, you can see that we have selected a steady time study because we didn't want our results to be a function of time. And the next part would be the gravity, which you can see it has been disabled because the simulation that we're going to perform here isn't very much dependent on the gravity. In the next step, I'm going to have to expand the model section in order to enable and define the needed modules for my simulation. In this project, since I'm going to only investigate the aerodynamics of a flying bird which is passing through the air, I'm going to have to only select and enable a viscous model. So I will simply double click on the viscous button, and in the shown window you can see that what I'm going to do here is that I will actually have to I'm going to actually select K epsilon model, and after selecting this model to solve for the turbulent fluid equations, you would be actually able to select among three options that are available for the K epsilon model. Now these three submodels, which are standard, RNG, and realizable, may have different accuracies. Regarding the accuracy of RNG and realizable, these two submodels are more actually accurate than a standard model. So for this project, I'm going to actually select realizable because it is more suitable for investigating the external flow behavior over different objects. And this submodel is much more accurate and appropriate to capture the flow wakes as it passes over different vols of related to the bird geometry. Next thing that we're going to investigate and explain would be the near vol treatment. As you can see here, different options are available here, and you can actually select among any of them. Now these are actually auxiliary functions that help you capture flow patterns near the vol and help you capture the flow velocity profile over the surface of different vol boundaries. As you all probably know, we have this no slip boundary condition over the vols, which states that the flow velocity is equal to 0 exactly over the in the vicinity of the vol. So these actually auxiliary functions help you capture the flow velocity profile near the vols. Also, another thing that is different between them is the y plus value. For example, for the standard vol functions, the y plus that is recommended for this vol function is set to be between 30 and 300. So after the simulation, you're gonna have to check your y plus value, and if the value of the y plus is between the 30 and the 300, as was mentioned earlier, then you're good to go and your results are accurate. And if not, you may want to actually go back to the meshing section in order to make your mesh cell smaller or even bigger, again based on the value that you are capturing for the y plus. Since for example, for the scalable vol functions, the range that is acceptable for the y plus is different than the range that you actually have for the standard vol functions. So I'm going to actually click on OK to keep this selected setting in order to solve for the turbulent fluid equations. Next, I will move on to the materials part. You can see that as I expand the materials, two different parts with the names of fluid and solid exist here. Since we are only going to investigate the fluid behavior inside our domain, the only material that is enough to manipulate would be the air. So as I actually double click on the air material, you can see its properties, which include density and viscosity in the shown window. You actually can change these values manually, and you can actually select your desired material from the list of available materials in the Fluent software, which are shown here. And if your desired material wasn't available in this list, you can actually define its properties manually, as was stated earlier. Alright, the next part that we're going to investigate and explain would be the cell zone conditions. As I expand the cell zone, you can see that this fluid domain is shown here, which is actually the domain that we gave name to in the ANSYS meshing software. As you again expand this part and then double click on the fluid underneath it, and as I double click on it, you can see that the material name part has the name of air material by default. Now this is because we only have one material under the fluid. If you actually had for example different materials other than the air material here, then you would have been able to select your desired material here. But since we only have one material, which is the air, there's no option available here, and the material name of air is selected by default. For the next part, which is the most important part, I'm gonna have to double click on the boundary conditions in order to explain each of them to you. Alright, in this part, which is again the most important part in this simulation, if I select, for example, inlet boundary, you can see that its type is defined as a velocity inlet. As I click on the edit button, in the appeared window under the momentum tab, you can see that the software is asking you for a velocity magnitude, which is the velocity of the airflow that is going to enter through the inlet boundary. So I'm going to actually enter the value of 40 meters per second. And regarding the turbulence part, you can see that the specification method of intensity and viscosity ratio is selected by default. Now regarding the turbulent intensity, it is defined as the ratio of velocity fluctuations to the mean flow velocity. And for internal flows, actually it can be calculated through the shown correlation, in which Reynolds dH is actually the Reynolds of a fully developed duct flow. Now the correlation is shown here, as you can see, and for example at Reynolds number equal to 50,000, the turbulent intensity value would be equal to 4% based on the relation shown here. However, for this project we're going to keep the default value here, which is equal to 5%, and move on to the turbulent viscosity ratio. Now the turbulent viscosity ratio is directly proportional and dependent to the turbulent Reynolds number. Now the turbulent Reynolds number is large in high Reynolds number boundary layers flow, and actually the range for the turbulent Reynolds number or the turbulent viscosity ratio is in the order of 100 to 1000. However, at the free stream boundaries of most external flows, like what we have in this project, meaning the inlet boundary of course, the turbulent viscosity ratio is fairly small, and typically the turbulence parameters or the turbulence viscosity ratio value are set between 1 and 10. So as you can see here, the software has automatically defined the value of 10, and we're going to keep it. Next, I will click on close and move on to the outlet boundary. As I click on this boundary, you can see that its type is defined actually as pressure outlet. I click on edit button, and then in the appeared window, the most important point that you have to pay attention to is the gauge pressure. As you can see here, the value that is defined here is equal to 0, indicating that the airflow will exit the computational domain to the atmosphere. Now, as a matter of fact, this gauge pressure value equal to 0 that is defined over the outlet boundary indicates that the pressure over the outlet boundary is equal to 0. I mean, the difference between the pressure of the outlet boundary and the atmosphere is equal to 0, meaning that the pressure of the outlet boundary is equal to the pressure of atmosphere. So that's it for the gauge pressure. And regarding the turbulence, you can see that the same specifications are defined, which have been explained earlier. Next, as I click on the symmetry boundary, you can see that there's no specific settings that you need to define, so I will move on to the bird vol boundary. In the appeared window under the momentum tab, you can see a stationary vol motion along with no slip shear condition are defined. Regarding the stationary vol motion, it is defined over the surface of the geometry of the bird. As a matter of fact, and based on the relative viscosity principle, you either can actually move the bird through the air, or you can actually move the air over the bird itself. So there is not much difference between these two. And since it would be hard for us to actually move the bird through the air with the velocity of 40 meters per second, so it is much easier to do the opposite and make the air flow over the bird surface with the velocity of 40 meters per second. So that is the reason we have selected the stationary vol motion. And regarding the shear condition, you can see that no slip shear condition is selected, which was previously mentioned and explained why we actually have to select this condition, because we assume that the surface related to the geometry of the bird are vols, and therefore based on the assumptions that the velocity of the air or any fluid would be equal to 0 as it flows over a vol boundary, then we have selected the no slip boundary condition. For the next part, we will move on to the methods, and in this part you're going to have to select a scheme or algorithm to solve for the pressure velocity coupling. Now, as you can see here, as I clicked on the drop down list, you would be able to select among 4 different algorithms that exist here. Now, the 3 top algorithms are iterative algorithms, in which the equations related to momentum, pressure, etc. are solved in an iterative manner while they are separated from each other using a correction equation. However, regarding the coupled algorithm, this algorithm solves all the included equations and parameters together. Now the coupled algorithm is much more robust than the 3 algorithms shown here. However, it uses much more computational resources such as RAM, CPU, etc., because it is actually solving all the equations together. However, for the simple or simple C or piezo, this is not correct, and you can actually use these algorithms when you have, for example, a not very great computational resources. So for this project, which is not a very complicated project, I'm going to actually select the simple, and then regarding the spatial discretization, these are the discretization methods that are used for different parameters that are included in your model. For example, you can see that for the turbulent dissipation rate, turbulent kinetic energy, the first order upwind is selected, while for the momentum and pressure, the second order discretization method is selected. Now, regarding their difference, the first order upwind, of course, as its name states, has less accuracy compared to second order upwind. However, its convergence rate would be much faster comparing to second order upwind, for example. However, its results, again, I should mention that, are not very accurate when comparing to second order upwind. So we're going to use a combination of these discretization methods and move on to the next part, which is the controls part. In the controls part, you can see that in the middle part of the software window, the software will ask you for defining under relaxation factors. Now you can see that the different under relaxation factors for different parameters are defined here. These values are actually between 0 and 1. And you may change these values when you are facing, for example, convergence problems or convergence difficulties. However, it should be mentioned that if you don't have prior or enough experience and knowledge regarding the usage of these under relaxation factors, it is highly recommended that you do not change them, because changing them without any knowledge and experience would and may result in divergence or actually inaccurate results. Alright, again, we're going to keep the default values for this problem, which are actually defined here by the software, so we can actually be sure about their accuracy and correctness. The next thing that we are going to investigate would be the report definitions part. As you all know, when you actually perform a simulation process, there would be residuals related to each of the parameters that are used in your model. And you can actually see whether your simulation is in a good state in the terms of convergence by seeing the residuals reaching and nearing zero. However, in order to increase your increase your However, in order to make sure that your simulation has converged, you can actually define different reports over different parameters. You can actually do that by right-clicking on the report definitions, going over new, and then you would be able to select among different types of report here. For example, surface, volume, force, etc. Now for projects in the aerodynamic field, the most important parameters that you can actually extract from a simulation and a project would be the forces that exist over your model. For example, as I go over the force report, you can see that drag, lift, moment, and other type of forces are available here. Let's say I would like to define a drag report. I click on it, and then in the appeared window, the first thing that you can do is to define a name for this report. After that, under the report output type, you are able to actually select between the two options of drag coefficient and drag force. As for the drag coefficient, if you would like to select this option, I should mention that you're gonna need to change the reference values and change, for example, parameters such as area, diameter, length, velocity, etc. to a correct value, so that the value that the software would calculate for a drag coefficient would be correct. It is because based on the formula that is obtained for a drag coefficient, you need to define, for example, a correct value for the area, so that the value that you calculate for a drag coefficient is correct. However, regarding the drag force, such thing isn't needed, and you can actually simply select this option and then select the bird surface zones and be sure about the correct value that the Fluent software calculates. However, before going any further, I should mention that the force vector section is another important part that you have to pay attention to here and enter a correct value for that. As a matter of fact, the airflow will actually enter the computational domain in the opposite direction of the z coordinate. And as you all probably know, the drag force is in the direction of the flow. So regarding the force vector, we have to actually change the value of x to 0 and enter the value of z to -1, so that the direction of the drag force that is calculated by the software is in the flow direction. The same can be said about the lift force. You all know that the lift force is perpendicular to the flow direction. So the value that you need to enter here, if you want to define a lift force, would be actually 1 for y direction and 0 for x and z coordinates. Since this is in a stationary simulation, if you actually click on OK and perform the simulation, you would see that the value for the drag force will start to move up from 0, and you can actually see that as we near the end of our simulation process, the value of the drag force would reach a constant value, indicating that our simulation has converged. But I'm going to actually leave that as an exercise for you, and I will actually click on cancel. However, when the simulation is finished, I'm going to show you the final value for the drag force or report, or actually any other type of different reports that we can define here. I will move on to the monitor section, and then I will double click on the residuals. In the shown window, you can see different parameters that are listed here, and in front of them you can see different values which are named as absolute criteria. Now the software assumes that whenever the residuals related to each of these parameters reaches a value less than the value that is defined under the absolute criteria for the respected parameter, then that parameter is considered to have to be converged. So in order to increase the accuracy of your simulation or model, you can simply, for example, decrease this value so that the number of iterations the software would have to go on would increase. However, your simulation results would increase as well. We're going to keep the default values, and I will click on OK, and I will move on to the initialization part. After double clicking on the initialization button in the middle part of the software window, you're going to have to select between two options of hybrid and standard. Now in the hybrid initialization, the software will automatically calculate the needed values for the initial values for different parameters that are needed to start solving partial differential equations related to that parameter. And those parameters would be actually calculated using the Laplace equation by the software itself. However, if you actually select standard initialization method, you get to define those initial values manually and by yourself. You can actually select these values simply by selecting a boundary under the compute from section. In this way, you will be able to define the initial values for different parameters more accurately, and hence you would be able to finish your simulation faster. So I will simply select the standard, and then I will select inlet boundary under the compute from section, and then actually I will click on initialize button. Next I will click on run calculations, and in the middle part of the software window, you're going to have to enter a value for the number of iterations you want your simulation process to be continued. It is totally up to you on how many iterations you want your simulation to move on, and of course you're going to have to pay attention to the absolute criteria that you have defined here. If all of the residuals related to all of the parameters shown here reach values lesser than these values, then your simulation would be considered as converged and would finish no matter how many iterations you have defined here. So I will simply click on select an enter value of 100 and then click on calculate. Alright, after the simulation is finished, it's time to go to the post-processing section where we will extract some graphical data and explain the physics behind each of them. For the first part, since our geometry and domain is in 3D, we're going to have to define a plane. In order to do that, before actually going any further, the plane which we're going to generate is the location where we would extract graphical data or other data on. So I'm going to actually right click on the surface, go over new, and then select plane. In order to show the plane, I'm gonna have to go to the general section, click on display, and let's just disable the edges part and also the symmetry. Alright. Let's say I would like to create a plane in the middle part of the bird itself, and the plane that I'm going to generate would be parallel to the XY plane. So under the method section, I'm going to change it to XY plane, and as you can see here, a shadow of the plane is now shown. You can actually define and enter the value for the Z, which will define the location of this plane explicitly and manually here, or you can actually use this arrow and just hold down your left click on the mouse and then drag your plane to your desired location. As I mentioned earlier, I want this plane to be exactly placed on the of the geometry of the bird. So I will have to simply drag this geometry to a location like this. All right, and then I will click on create. After that, I will go to the graphics section and then double click on the contours button. Under the contours of section, you actually, if you click on the drop down list, you can select among different and multiple options and parameters that exist there. Let's say I would like to first extract the velocity of the flow over the generated plane. So I will have to click on velocity, and under the surfaces section, I'm gonna have to select the plane that I've created. Before actually clicking on save or display button, we're gonna need to disable the global range. In this way, the values that are shown on the legend of the contour would only relate to the contour that is generated over the plane itself. In case if we actually let the global range be enabled, the values that are shown on the legend denote to the whole domain. So we have actually disabled it, and then I click on save or display button, and now you can easily see the, let me just change it into the, and now actually you can see the velocity changes over the surface and on top and bottom part of the bird geometry. Now as you can see here, based on the darker red color that exists on the top section of the bird, you can see that the velocity of the airflow is much more than the velocity of the airflow on the bottom part of the bird wings, which is completely accurate and correct, since the shape of the bird wings are similar to a airfoil, and the velocity of the air that is passing, for example, over the top surface of an airfoil is much more than the velocity of the airflow passing underneath it. So this is actually the velocity distribution around the geometry of the bird. And if we want to, for example, extract another contour or extract another contour related to another parameter, you can simply change it from the contours of section. Let's say this time I would like to see the pressure distribution on the generated plane. So I'm gonna have to simply change the contours of section to pressure, and let's just keep the plane number 5 as the selected surface, and then click on save or display button. Alright, as you can see here, the pressure of the airflow on top part of the wings of the bird is lesser than the pressure of the airflow on the bottom part. And the reason actually was explained previously, which is due to the fact that the velocity of the airflow on top part of the bird's wings are much more than the velocity of the airflow on the bottom part, due to the actually shape of the airfoil, as was again mentioned earlier. So this is pretty much that we could actually extract from the two contours of velocity and pressure over this plane. However, we can actually create another plane in order to see some other data. For example, how the the velocity or the velocity of the airflow has changed after it passes over the surface of the bird geometry. Or we can actually extract some data related to the pressure distribution over the surface of the bird geometry itself, which we will investigate in no time. So in order to create another plane, again I'm gonna have to click on new, go over plane, and this time let's say this is the plane that I would like to have for my geometry, which is exactly the kind of plane that I wanted, because it passes from the middle part of the geometry of the bird, and it is parallel to the YZ plane. So I'm going to actually keep this and click on create. Okay, I will go back to the contours, and let's just keep the pressure contour here selected, and just change the surfaces from plane number 5 to plane number 6, which is the newest plane that we have created. I will click on save or display, and as I rotate this geometry, you can easily see the airfoil shape of the wings of the bird, and you can easily see how the pressure has decreased on the top part of the wing while it has increased on the bottom part. Also, you can easily see how this leading edge of the airfoil or wing has an increased pressure in comparison with the other parts, which is related to the stagnation point where the airflow will reach an stationary velocity, or actually question the state when it actually touches this point again, which is called the stagnation point of an airfoil. Alright, let's move on to the velocity of the airflow and capture it. Again, you can easily see the velocity of the airflow has reached the value of 0 on the surface of the wall boundaries due to the no slip shear condition. And if you actually pay attention to the changes in the velocity magnitude, although it is subtle, you can easily see that it has reduced value and decreased value, actually indicating that these are the locations which are susceptible to possible flow separation. Which if we actually increase the airflow velocity that is entering from the inlet boundary, you would be able to see vague regions behind this airfoil. So let's just move on to the turbulence part and extract wall Y plus. This is a factor that we actually explained in the earlier part of the simulation, and we mentioned that if it falls inside a correct range, then the choice of auxiliary functions were correct. So let's just calculate it, and let's just keep this value, let's just keep this plane number 6 under surfaces selected and see the changes of the wall Y plus. Alright, as you can see here, the value of the Y plus that we have over the surface of our wing is between 0 and 152. Now regarding the maximum value of Y star falls in between the two mentioned range. However, the minimum part is less than 30. In computational fluid dynamics, when you want to actually calculate the value of the Y plus and see whether it falls into a correct range, you need to actually extract the mean or average value of the Y plus. So in order to do that, we can actually go to the reports, double click on the surface integrals, and change the report type to area weighted average. And as for the field variable, you just have to select turbulence as we did for the contour section, and then underneath it we're gonna have to select wall Y plus, and then we either can select the eagle surface itself or the plane number 6, which we would of course select eagle because it would be more accurate in terms of calculating the Y plus over the wall boundaries. So I will select eagle, and then I will click on compute. As you can see here, the area weighted average, or the average value of the Y plus, is equal to 102.57, which is completely correct in terms of falling inside the correct range due to the let me just show you, due to the fact that we have selected a standard wall functions near wall treatment. So this tells us that this value tells us that the simulation that we have performed here is completely correct in terms of wall Y plus value. Alright, as was mentioned earlier in the process of defining needed settings, we mentioned something about different reports that you can define, which was, for example, force, such as drag, lift, moment, etc. In order to calculate the final value related to these forces, you can actually go to the forces section, and then as was mentioned earlier, if we, for example, want to calculate the drag force, and as was again mentioned and stated earlier, let me just show you the geometry of the bird. And let me show you the output lines so that you would be able to fully comprehend the direction of the flow. So as you can see here, the airflow will exit from the inlet boundary, which is placed on this part. Actually, I haven't shown it. And will exit the computational domain through this boundary, which is the outlet boundary. So you can easily understand that the airflow direction is in the opposite direction of Z. So in order to correctly calculate the value related to the drag force, you're going to have to enter the value of 0 in front of X, while entering -1 in front of the Z, which was of course earlier stated and mentioned. And of course, since we would like to calculate this drag force over the surface of the, for example, the bird, I'm going to actually select eagle under the vol zones. And now as I click on print, you would be able to see the details related to the drag force that are calculated over this surface. On the console tab, you can see that the drag force is divided into two main parts, which are the drag force due to the pressure and the drag force due to the viscous tensions. Now you can easily see that it has described the value of drag force for each of them, along with describing a total value of the drag force, which is the actually summation between these two values. Also, the software has given you the reports related to the coefficients of the drag. Of course, this coefficient would be related to the drag. However, it should be mentioned that the values that are printed here are not correct due to the fact that the values that have been defined under the reference value section are not correct. So if you actually want to correctly calculate the values for drag coefficients, you're going to have to make sure that the values that are defined under the reference value section are correct. And you can actually obtain more information on that by searching inside the internet and looking for drag coefficient. Alright, this is for the drag force, and for example, let's say if you would like to calculate the lift force as well, since the lift force is perpendicular to the flow direction, then its value would be in the Y. Then its direction actually, should be in the Y direction. So we're gonna have to change the value of Z back to 0 and change the value of Y to 1. In this way, the force that we are calculating would be the lift force. So after I click on the print again, the value of the lift force that are reported here are shown now. This is the lift force due to the pressure tensions, and this is the lift force due to the viscous tension, and the value of total lift force, which is the summation between these two, are now reported here. The same thing can be said about the lift coefficients, and if you would like to calculate the correct values for the lift coefficient, you're going to have to again make sure that the correct reference values are defined here. To benefit from MR-CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com, or please visit our website www.mrcfd.com.